My name is Jeremy Crookshanks. I'm product manager for hydraulic and lube filtration. Today we'll be going through tank optimization, next generation filtration. I know we've talked about tank optimization a lot in the past, but it's one of those things that kind of keeps evolving, and you'll see some of that as we work through this presentation today. We I guess we'll go through all of this. If you have any questions, feel free to drop them in the chat window, or hold them to the end, and make sure we get all through the entire presentation, and then we'll take it up from there with any questions at the end, or if I happen to see them as we're going through here and I can work them in, then I'll try to grab them out of the chat window. So, all right. So here's a little bit about the agenda. We're going to go through tank optimization background for anybody who might be new to this concept. The next thing we'll talk about is the 2030, 2035, 2050 kind of CO2 reduction pledges that different corporations and stuff are using. They're all kind of the same thing to reduce their carbon footprint. It's just everybody has kind of a different year associated with it. So we'll talk about what's going on there and what we're doing as far as our part. The next thing we'll go through is pairing tank optimization with the next generation filtration, and what all are required there. And then also pairing that with the complete tank systems, tank and system solutions when it comes to Schroeder Industries with filtration and the ability to add cooling and that kind of thing as part of an entire package, and some stuff that we're working on here at Schroeder Industries. So the first thing we'll talk about is kind of the tank optimization drivers. So when we first started this tank optimization program, the thing that we were really the most up against was the Tier 4 legislation. With the more lower emission Tier 4 final diesel engines. They had to put a pre-cleaner and after cleaner on those units to clean up the exhaust from the diesel, and that just made the engine compartment larger, left less room on your mobile equipment to put things like a hydraulic tank and all of your hydraulic components and everything. So size kind of became a something you're really up against. The next driver that we're going to see coming down the line is going to be the zero emissions vehicles and those requirements. So we were at the work truck show this year in March, and we went to what they called the Green Truck Summit, and the Green Truck Summit was just really a layout of what all's coming as far as the zero emissions vehicles, whether that be electric or hydrogen or hybrid, or something along those lines, or something new they haven't even thought of yet. We don't know. But what they really showed there was that on your standard Class 8 truck, the battery itself is going to be 2,000 pounds heavier than what a standard diesel engine would be. So anywhere, if you're adding that much weight to these units with batteries and everything, anywhere you can save weight and space is going to be key. And then so that's really one of the things that's driving us and our push to help customers with their CO2 footprint and their tank reduction and optimization needs. Obviously, global competition is there, energy efficiency. Whoever has the smallest battery that gets the most work. The smaller the battery, the less expensive the machine. So if your machine is more efficient and you can run a smaller battery for the same duration, that's going to be a big selling feature for your machines going forward. So, there's a lot that really plays into it. If you don't do it properly, it could lead to a lot of reliability problems, and that's where we at Schroeder Industries can step in and help you look at that overall system from a tank optimization standpoint. So, come on, computer. All right. So I kind of mentioned before, at Schroeder we have something up on our website called the Schroeder 2030. That's just kind of the first round of initiatives that people are laying out. The California initiative from CARB is a 2035 initiative that they're working on, and then I've seen a lot of OEMs and stuff and big business have some 2050 pledges. So kind of the same thing, reducing your carbon footprint and doing what you can to help clean up the environment. And regardless of what year they pledge to do it. So this graph over here on the right is one that we like to show. It really shows the volatility of the fossil fuel market versus the cost of electricity. So you know you know the electric generation plants, whether they be on clean energy or like hydro or solar or anything like that. They can pick and choose kind of, or not, sorry, um, regardless of the renewable energies, your standard power plants these days are tri-fuel burners where they can burn any number of fuels, whether it be propane or CNG or LNG, depending on what the lowest market rate is for that particular fuel at the time. So that's what keeps the electricity costs very low, regardless of the variability of those fuels. So that really brings along a lot of the push to go to electric is just removing the variability of that fuel cost. There's also a bunch of initiatives and everything. This is kind of the subsidies and things that California is putting in. 256 million in low income ZEVs, zero emission vehicles. 540 million to retrofit their transit, 600 million for over the road trucks and buses, and this is just kind of the start. 250 million in their ports. So and that doesn't even include what the new National Climate Act that they just put in place this week. I guess the powers that be will be spending the next few months going through that and seeing where the subsidies are and what's going to be the drivers for that legislation and where it's going to go from there. So that's still pretty new, but it's something that we'll definitely be keeping our eye on. Um, um, a lot of people like to say that um, this kind of stuff is just a fad. It'll never take place in my lifetime, that kind of thing. But that's just simply not true. This chart up here on the right, that shows all of the new battery plants that have been announced and are a lot of them under construction already, or at least in the planning phase for the big OEMs and everything. Ford, General Motors, SK Innovation, which I think they sell a lot to Dodge, and maybe Toyota. But they're also Toyota's also building their own one down outside of Greensboro. So, they're really making the investment into these, new battery plants, and this stuff simply isn't going away. Another thing is, you hear 2030, 2035, 2050. This lower chart here, this is the CARB, California Air Research Board chart of what is required in the state of California. So starting as early as 2024, they will be requiring, if you sell vehicles into the state of California, whether it be class 2, class 4 through 8 or class 7 and 8, that this is the percentage of vehicles that have to be zero emissions at that year point. So, if your OEMs are selling into California, which it's a huge economy, I think um, we were just at the NFPA um, um, Economic Outlook Conference, and they were talking about the Russian economy and the size of it and everything. And the California economy alone is larger than the complete Russian economy. So just the state of California. So that economy is a piece that everybody wants a part of, and um, they're going to be required to be in compliance with these percentages. So, as the years go up out to 2035, they're going to expect that, on these classes of trucks, this is the percentage, 55, 75, and 40% of these trucks are going to have to be zero emission, whether that be um, um, battery or hydrogen um, or whatever else it might be going forward. So that's just kind of the layout and where this is going to go. So this just points to, these things are going to be coming down the pipe sooner rather than later. So, um, you know, at Schroeder Industries, we don't believe that, really on a lot of vehicles and stuff, we think it's probably going to start in some sort of hybrid model. So this is kind of a hybrid model where you end up with a diesel engine turning a generator at at a constant RPM that's the most fuel efficient for the engine. This is going to show significant CO2 savings versus ramping idle up and down to run the hydraulics and everything. So, what they can do is they can then dispatch this power either out of the generator or out of the fuel cell or battery of the machine, to these direct drive units on the hydraulics. So this is just an example of what would be a very efficient system um, from a hybrid model. One thing that we've seen on our end is, we have a lot of OEMs that are looking at the battery powered stuff, but right now, the batteries themselves are just cost prohibitive for the marketplace. So we were at a major OEM a few weeks ago, and they were talking about um, their battery powered machines, and their battery powered skid steer was going to be 208% more expensive um, than their current skid steer. So at 208%, that's really a barrier to entry into the market itself. So that could cause real problems with their bottom line if they try to switch to that too fast. But they anticipated in the next 5 to 7 years so that the prices of the batteries themselves are going to be coming down, especially with all of those battery plants going online, and just getting more out of the market, and more market competition, and more innovation in that market as more of the companies come in. Right now it's been kind of a few of the big guys like Tesla and whatnot, and a few handful of startups. But when everybody is out into manufacturing batteries, that price is really going to come down significantly. Um, so just an example of what we're looking at, and then um, what we're going to need going forward. So next thing we'll start talking about is our tank optimization. So this might be um, redundant for a lot of you guys who have talked about the tank or heard about tank optimization before, but it's a brief overview. So we'll go through this for the rest of the people in the crowd. So when we start with our tank optimization, we look at the flow, we look at the deaeration, we look at the sloshing, we can look at thermal conductivity of different tank materials, and then we also look at structural if necessary. So This is kind of where we started with tank optimization. And we kind of initially started this thing about 10 years ago. You trying to use our existing filters to make our customers' machines and reservoirs more efficient, and then through that, we've came up with better mousetraps as far as the overall filter itself goes, and we'll be walking through a few of those examples and a few of those products as well today. So this is kind of a quick example of um, what a typical customer tank that comes to us sometimes looks like. A lot of the times they have their hydraulic reservoir, they have their suction strainers over here, their filter has to come in here because of just the machine architecture. So they put a 90-degree down tube here, say, all right, I'll push my flow away from the suction strainers. That'll give more resonance time in the tank for deaeration and everything, and then I should be good to go. Well, what they basically did there is it bounces off of this wall at a very high velocity, you know, circles up and then goes right back down to the suction strainers. Um, so this is kind of where we started with these projects. We could add some very simple baffling and everything, and being able to reduce the size of these reservoirs. But as we looked at these more and more, you know, we came up with new filters and everything that we can use to additionally reduce the size of these reservoirs. So, the first thing we look for are dead zones in reservoirs. So, right here's a big dead zone, and if you see an area of a tank that has a big dead zone with no mixing, then you really don't need that volume and that area in there. So, that's one thing that we found. That's the first thing we look for, and then we look for other ways to improve and reduce. So at Schroeder Industries, we're the only place that I know of currently that has the ability to do both the CFD, the FEA, and then the physical testing of the reservoirs. When we first did this, a lot of people wanted to see the physical testing and the side-by-side analysis. They didn't really believe the CFDs and stuff as much as they do now, the computer flow dynamic models and everything like that. But now, I think as high-end computing and everything like this has become more commonplace. A lot of the time, pretty much everybody trusts the CFD. We've also done, you know, looking like staring at down the barrel of I don't even know anymore. Between I'd say at Schroeder Industries alone, we've done probably upwards of 125 CFD models and tank optimizations for customers, and not one time out of that 125. Um, well, not all of them went to fruition, but of the probably 50 or 60 we have running in the field currently, um, we we've not had one customer come back to us and say, "Oh, this doesn't work on our machine. We have to upsize the reservoir another 5 gallons to get it to work." That's just simply never happened. So it is a very safe and consistent technology and everything that we're bringing to the customers. So this is what it looks like on our you know on our on our physical test stand. So what we would do is we would be able to hook up, tank A, which is our optimized tank, and then tank B, which would be um, the customer's baseline model, what they're currently using now. We can inject air into that test stand, and we can see with our turbidity sensor exactly how long it takes for that air to dissipate out of the reservoir. So, ideally, you want that air dissipated out as quickly as possible. So, we'd be able to show customers very good results with that layout and with that technology. So you walk into a customer and they're not sure if tank optimization is right for them. Um, so these are kind of the key tank utilization indicators that we look for. So, the first one we look at is tank turnover ratio, which is your pump volume or your max return flow rate versus your volume of your current reservoir. If the tank's already turning 4+ times a minute, probably not a good candidate to reduce volume. But a lot of the times we go in and the old hydraulics and pneumatics handbook from back in the day, it says that um, you should use 2 or 3 to 1 rated pump flow as your hydraulic reservoir size. So um, if you have a 50 gallon a minute pump, then you should put a 100 or 150 gallon reservoir on your hydraulic unit. But nowadays, with hydraulic coolers and more efficient piston pumps and everything like that, and hydrostat technology and everything, that's simply not the case anymore. So there's a lot of people that don't believe that, but we have customers running a 2 to 1 50 gallon a minute pump with a 100 gallon tank is a half turn per minute. We have customers running 6 and 7 turns per minute, depending on the application. Obviously, 7 turns is a very intermittent duty cycle, but a lot of our customers, we can get them to 4 turns per minute and continuous duty operations. The next thing we look at and this is really um, the key to how much we can reduce a customer's reservoir. If you look at your uh, system volume required, so if there are some large cylinders on the machine, we probably can't reduce the volume a ton, but we try where we can to at least increase the performance. So if it's on a crane application where they have some very large cylinders on here, we might not be able to reduce that application, but the majority of our customers are, if they're running like a 30 or 40 gallon tank, their cylinder drawdown volume is usually like 5 to 10 gallons, and in those situations we can usually reduce the size of the reservoir by roughly half. With those cylinder drawdown volumes, if they're running 5 to 10 gallons, we can take them down to a 20 or 25 gallon tank from a 30 or 40 gallon tank pretty easily. So um, just looking at system volume required. The next thing we also look at, filter type and location. You know, spin ins and inline stuff is sometimes necessary for the application, but if we can get it moved to an inline or to an in-tank filter, and reduce the complexity of hoses and piping and things like that, we can save the customer some money. And in-tank filters just typically, especially the next generation in-tank filters, um, uh, operate so much better within the reservoir than they do as the standard inline filters would, like a spin on or something along those lines. The next thing we can look at, we've ran into a couple of customers that have a bad enough issue that where they have cloudy fluid and they need some help to clear that up. Um, but typically, um, customers don't have that problem, because if it's an aeration problem or something like that, they generally just upsize their tanks, so they don't have so they don't have that big of a issue. But upsizing that tank costs them more money in oil, more money in steel on every machine. So if there is cloudy fluid there, that's usually a pretty good indicator for ourselves, for us. So the Schroeder approach. Like we said before, we kind of started this program, trying to use our current or previously existing filters in customers' reservoirs to optimize them and reduce the reservoir sizes and just make the reservoirs perform better with that. But over time, we saw some things with our own filters, and we saw some things within the CFD models that said, the slower you can get that fluid entering the reservoir, the less entrained those air bubbles and the aeration can be and the faster those, the smaller air bubbles will group up together with larger air bubbles and rise to the surface of the tank. So, we spent a lot of time and effort and research projects on kind of redesigning what some of our traditional filters look like and how they perform. So down here you see the BRT filters. These are our highest performing deaeration filters. And it's called a BRT because it has a bottom return inlet. It looks a little unconventional to a lot of people when you first see that, but those bottom return inlets, those allow the hydraulic fluid flow to naturally push the air bubbles and everything to the surface. So as the fluid comes in the bottom, it's kind of giving you a natural effect of pushing that hydraulic fluid to the surface of the reservoir at a very low flow rate because it exits the filter itself through these patented deaeration windows that slow down the volume and help with the coalescence and help that rise to the surface of the reservoir in a 360-degree radial pattern there. So it really helps to reduce that overall velocity coming out of the filter. So the BRT and then the TRT, this is the kind of the top return version, which is more standard that you would see in customers' applications and everything today. We we went to that same type of setup because some customers just can't wrap their heads around it and adapt to using these bottom return filters. So we also have the top return with the same kind of deaeration window and everything that are on there. And then this new one over here is the AFT filter. It's kind of the little brother to the TRT, and it's a top return, but a lot of injection molded parts and everything, and we can actually mold this ring itself into a road molded tank to help further reduce the cost of the unit going forward. So um, and then we also have these available to pair with the eDrive media. The electric drives, like we talked before, the more you can increase the efficiency and decrease pressure drop, the less energy you're going to burn. And if you're looking at a 50 horsepower, 100 horsepower application, it doesn't take a whole lot of pressure drop through a system to really eat through some dollars in a given year of electric. And this was running obviously continuously, but it's just one of those things. Um, so talking a little bit more about the BRT, I touched on it briefly, but it's the bottom inlet. You're coming up through the middle of the filter, out through the media itself, and then out through these patented deaeration windows. Bypass and everything is built into the cap. Also has an anti drain valve in the bottom of it, so when you remove that element, all of that dirt and contaminant stays trapped in the inside of the element as you pull it out of there. Nothing is falling back down into your tank and contaminating the hydraulic reservoir over again there. So we'll go through a quick example on a customer tank that we did with moving them to the BRT filters. So this is the customer's current reservoir. As you can see, it's a little bit complex, and it's kind of indicative of a good bit of OEMs from what we see is, they just kind of mount on and add on things as their machines become more complex and needed additional higher flow rates and things like that. So they just kind of been mounting onto this thing. But as you can imagine, this is a very expensive reservoir to build with one, two, three different filters on it, these brackets and manifolds and everything. So, this is a very good example of where we can really help the customer reduce size and weight and cost overall. All right. So, one thing to um, touch on here is that with our tank optimization programs and everything, the analysis is typically a comparative analysis, meaning we take their baseline simulation tank and then we do our optimization, and then from our CFD to the from on the baseline to their new CFD, we just try to improve those overall results. And if we can reduce volume and improve the results, that generally means to us that that's going to be a safe simulation and not cause the customer any problems with their reservoirs or on their machine with any overheating or anything like that goes on. So in this simulation, they're running at 69-gallon volume. We're simulating it at 44.2 gallons. That includes that 10% air gap that's typically designed into the top of your tanks and the cylinder drawdown volume. So you're looking at about 15 gallons overall. Uh, Empty space in the tank. Obviously, this was the kind of the worst case scenario. If the cylinders are extend or retracted and this has more volume in it, then obviously it's going to function even better. So that's more or less the worst case scenario for the units themselves. So we tested this at their baseline, and we pulled the deaeration numbers. So we inject 2 and 3 millimeter air bubbles, and we aim for 85% and 95% reduction of those air bubbles. So with this unit, we got to 81 and 92, which isn't by far the worst reservoir that we've ever tested. But it does just show that we have room for improvement overall. So, um, so we went in and we went from their 3 filter layout into a 2 filter layout with 2 of the BRT4 filters to handle that 200 or roughly 160 gallons a minute that they're running. We were able to, with this filter and these iterations, we were able to reduce the size of that reservoir another 20 gallons overall. Um, and by reducing that reservoir 20 gallons part of the tank, that's 3 cubic feet of machine space. So 7 gallons of hydraulic fluid is roughly 1 cubic foot of machine space. So um, significant room savings on their vehicle as well. And then again, operating at that 160 or so gallons a minute. So even with their reservoir at 20 gallons less, 29% volume reduction, we're able to reduce or increase the optimization the deaeration of their tank, and show an overall better performance than what they are running before. So another reason that we view these simulations as relatively safe is because within the CFD we don't have the ability to simulate the coalescence of the air bubbles. So when we inject a 2 millimeter air bubble, it stays a 2 millimeter air bubble. When in real life, it should group up into two 2 millimeter air bubbles, make a 4 millimeter air bubble, and they rise to the surface even faster. So these simulations would be on the conservative end, as we tell people when we um, run these simulations. So Um, other things. So kind of everything, every time that we do one of these, well, maybe not every time, but I've always said it for a long, long time, but a lot of the best ideas come from the customers themselves. So we did one of these on a trenching machine just a few weeks ago, and they were excited to reduce the size of their reservoir because they could heat the oil up faster. So, when they shut their machines down at night, they can't operate their machine again until the oil gets to a certain temperature. Some of their controls and stuff just don't work correctly until the oil is heated up. So they kind of got to start the machine up and circulate the oil um, to heat it up long enough to get their machine to operate right. So by reducing the size of their reservoir, that's going to cut down that idling time and that heat up time on their machine, lower their fuel cost, everything like that. So it's one of those things. It's every few times that we do one of these things, we come up with a new advantage that we maybe hadn't thought of in the past. And just last week, somebody sent me one that had a calculation on it that I hadn't taken into effect, was the cost to ship the tank. A lot of these customers will buy from a tank manufacturer, and a lot of the tank manufacturers are kind of in middle America. Um, and they get shipped all over California or East Coast or something like that, and the cost to ship that tank, when it's reduced size and weight, goes down as well. And that's something that we'll be, kind of working into our calculations as we go forward. But, every time we run through these things, we find something different. This one, the one we didn't anticipate, and the customer pointed out to us, was it was a better field of visibility for, and this is the one they were most excited about for their operator than their current 69-gallon tank. This hydraulic tank sits right behind the operator cab, just the way their machine lays out, and um, and so as that sits behind the cab, he really couldn't see over it as well as they can now with our reduced height tank. So that was a big win for them as far as that's concerned. Obviously, lower cost of ownership. 20 gallons hydraulic fluid every time you change it out. And this was back when hydraulic fluid was $7 a gallon. Now it's probably $10 or $12 a gallon. So this is probably $200. Can fill from single gallon drum reservoir. Hydraulic warranty claim decrease with the lower air content, and then increased machine uptime. These are kind of the intangible ones that are hard to prove, but anytime something functions better and you improve the performance, that's what you're going to get from a hydraulic standpoint. Um, so we talked about the zero emissions vehicles. We talked about the 2030 stuff. So if you go to this U.S. Energy Information Administration website, they have some calculations on there for kind of how much CO2 it takes to produce a gallon of hydraulic oil. Well, I call it non-fuel oil, but we'll take that as hydraulic oil at this point. So, it costs roughly, I think the number is roughly 23, it takes roughly 23 pounds of CO2 um, to um, to create 1 gallon of oil. So if you exclude 1 gallon of oil from your hydraulic reservoir, you're going to reduce that by 480 pounds of CO2 that is put in the atmosphere. So, if you're building, 100 machines a year, which isn't a lot for a lot of these OEMs, you're talking 48,000 pounds of CO2. It's not huge when you talk about the amount of global CO2 that is dumped into the atmosphere every year. I think it's in a number in the billions, um, maybe even trillions. But I think, as we start thinking like this and we start helping OEMs and everybody with it, and everybody, sticks to their pledges and works towards this common goal, You just think about how many OEMs are out there, and if every machine that goes out the door is 480 pounds of CO2 lighter, then that's going to, end us up in a better place as far as um, cleanliness of our environment and reducing, the overall carbon footprint of everything. So on this unit, we're also able to save 280 pounds of oil weight and steel weight, which leads to which leads to better fuel economy on the machines themselves um, when they're in transit mode. $140 worth of oil savings per machine, and overall on this reservoir, we're able to save them $988 from this very complex unit to this much more simplified unit, and increase the performance and show a lot of other tangible and intangible ROI for this application. So it's kind of a win-win, all the way around. And like I said, as we do more and more of these and talk to more and more customers, we find, just you know exponentially more benefits to our customers all around. Our hope is that by doing these things, we're partnering with the customer, we're showing them how we can help reduce all of this stuff on the machine: weight, cost, CO2, carbon footprint, all that stuff. And we have a couple of OEMs now. At this point, we've done a couple of simulations for them, and they basically came to us and said, we kind of don't have anybody on staff that knows how to design a hydraulic reservoir anymore, through turnover and attrition and early retirements with COVID and things. They're like, can you guys just help us design all of our reservoirs? And we're like, sure, gladly. That's what we're here for. So that's the kind of partnership we want to work towards with our OEMs and our customers overall. So um, this next filter we'll talk about is the AFT filter. Stands for Air Fusion Technology. That's kind of the trade name we're given to a lot of these um, air reduction filters that we're working on running. We'll go through this, but this one's set up to kind of be the little brother to the TRT and the BRT. It's 40 gallon a minute. Those other filters are upwards of 75 gallon a minute on the small side, or 50 gallon a minute on the small side. So into outflow to give you that nice smooth mixing within the tank. So the key to this filter is when we tested it in the lab, it dissipated air 55% more initial air dissipation than your traditional in to out flow filter, or out to in flow filter, with where it just comes out of the bottom of the filter kind of like a flow jet. So this kept kind of those air bubbles from ever making it to the suction strainer that first time, which really is the goal when you have an air event within a hydraulic system. The faster you can dissipate that and keep it from even going through the hydraulic train one time, the better it is for the overall system, and the less damage you're going to cause to those sensitive components like piston pump swash plates and that kind of thing. So there's a lot of kind of technology built into the AFT. It has it has a fully injection molded support tube inside of it, but then also on the outside we have this deaeration layer that really helps with that. On the next slide, we'll see that some of the competition, they have into outflow filters that kind of resemble these, but they have the support tube wrapped directly against the mesh pack of the element. When you direct that, or when you wrap that directly against the mesh pack of the element, what you're gonna come into is there's no when it comes out of that mesh pack at 10 micron or whatever media rating you're at, it goes directly into the tank at that small of an air bubble size. There's no there's no resonance time. And even with this, small amount of space here as it comes out, it really helps to um, um, ramp up that coalescence on on the on the air bubbles there. So also up here, our we have a top bypass, and these windows in the top of this thing allow that bypass flow when it does go into bypass to at least go through these windows and down through the aeration layer and keep that high performance of that filter, even if it was in cold start bypass or something like that. And if you think about it, a lot of these um, machines have their biggest problem right when they start up, you know, um, and when they start up, the oil is cold, but lines have drained, maybe back drained into the tank or something like that, so they have a little bit of air in the system from that kind of thing. And when they start up, there's some air in there that gets spit through here, and if it's mixed with cold cold oil, then it's going to go through the bypass, not through the filter itself. So this allows that performance to stay high um, regardless of when the air is entering the system, whether it be in a bypass setting or straight through the element. So another thing, you know, one of the some of the competitors do is they put their bypasses in the base of the element. As you can see here, what happens there is that all of that debris and everything deposits itself down on the bypass plate or the dish of the bypass, and then as soon as there's a cold start, all of that dirt just flushes right back into the tank, and you're kind of back to square one, trying to catch it all again, and it's flowing through your system, causing the damage that it typically causes. So you can see here, just in different runs of this, in cold start with the competitions versus ours. Much cleaner overall operation on the on the cold start application. And you know, this is what it looks like as I was saying before. A lot of the competition, um, they'll have the outer wrap. It's perforated, looks like this, but they'll have it wrapped directly against the media. And what that does is it doesn't give you any real deaeration layer to that filter. So even on a filter like that, that gets the radial dispersion of the oil and the lower velocity, it doesn't um, perform nearly as well as what our new AFT filter does. And this is just a quick video of one of these things operating. I don't know. If I click the oops. I don't know if I click the sound button or not, but um, so anyway, you can see in this application, just it's basically creating air as it pours down into the reservoir itself. So sizing this and where it goes into the reservoir is the most important. There's there's these injection molded support tubes. So that's what supports the actual media itself, is these injection molded support tubes, and then the outer wrap is actually there just for the deaeration aspect of that. It's not there to to support anything. It helps provide that on air bubbles and start making them larger as they go back into the system. So, All right. So this is a quick just illustration of what the AFT looks like against the like a spin-on competitor. A lot of the time this is in a 24-gallon minute and a 12-gallon tank. A lot of the time with spin-ons they're just direct flowed right into your tank, kind of as that flow jet like we talked about. Bounces off the wall of the tank itself. Um, a very high velocity causes a lot of issues. Um, you know, when we see red like this at the surface, we know that there's a potential problem because surface velocity is above 0.8 meters per splashing everything 2 millimeter and 3 millimeter air bubble on something like this is very poor performance overall versus versus an in view flow mixing and everything within the hydraulic reservoir. Um, you can see that there's really no velocity at the surface, so a lot smoother overall performance. And then, you know, excellent performance characteristics of the reservoir itself. The 1 millimeter air bubbles are really so hard to remove because they're so small. And like I said before, we can't simulate the coalescence of them into bigger air bubbles. So, 60-70% is generally as good as you get with the really small air bubbles. But 99% on the 2 millimeter and 100% on the 3 millimeter. So really excellent performance overall. So that's what you're getting when you go from something that's in line or a poor reservoir configuration, just one-to-one with a next generation, really optimized filter that gives you a lot better results and a lot better performance. Um, the next thing we're going to talk about is the TNK platform. So the TNK platform, we kind of launched this TNK platform before we launched a lot of the next generation filters, but we have some stuff in the works to add the AFT to the 7-gallon tank and the 12-gallon tank to start with. Um, uh, but so we've quoted a couple that way, and we're working on new tools to implement that. The problem with the rotomotive stuff is once you make the tool, you're kind of set with the tool. So we need to buy some additional TNK7 and 12 tools anyway. So they will be equipped with the ability um, to include the AFT filter in those tanks going forward. And then the TNK25, we can already add one of the TRT sizes to that as well for in increased performance. But we designed these reservoirs after we'd already started the CFD program. So they already have a lot of optimization built into them, even to help use our existing filters as good as possible. So they're still a very high performing concept, even though they don't have some of this next generation technology in them as of yet. But that is something in the works. So optimized, ideal for small to medium OEMs that want to look at plastic as overall weight savings, but don't have enough quantity of their own. Numerous options, you know, they're clean. A lot of people have problems with weld slag and stuff like that from either making their own hydraulic tanks or buying hydraulic tanks from people that don't actually know how to clean them. We at Schroeder Industries are a hydraulic filter company, so we really understand the importance of clean, whether it be the wetted side components of our filters or the overall hydraulic tanks themselves. And then also available with water protected elements like the GeoSeal and the lock and key, which is built into the um, AFT filter itself. We also have the ability to integrate and add components with these. Here's one with a cooler mounted into it. That's for really, needing to save as much space as possible. And when you can mold, the nice thing about rotomolded tanks is you can um, mold them around different things, and you can mold them into shapes that you literally couldn't fit a weld head or welder head into. So if you have customers whose space constraints are very tight, you can look at something like this with the rotomolding line and really amp up your options as far as that goes. They also get molded into fender wells, all kinds of different shapes and sizes and everything as far as that goes. We actually do the rotomolding at Schroeder Industries, 100% in-house. This is a picture of our machine. We just got that last June, and since then, I think we've made I think we're working on 3 or 4 thousand of our own tanks out of that machine. So at this point, um, we really know what we're doing, and we're really ready to tackle about any application that people can throw at us. Um, so this is a application for uh, fire truck. So, we get a lot of customers come to us and say, "Hey, do you have a TNK 50? Do you have a TNK 30 or 40 or something like that?" And the reason that we haven't tooled up for a larger one like that in the 40 or 50 size is because we really haven't needed to. So this application here, they're running basically two different 60-gallon tanks. I'll only show you one because it's kind of redundant, but they're running two 60-gallon tanks, but they're only running it 48 gallons a minute, so a little over 1-to-1 turnover ratio. But with their current setup, they have an inline filter that just directs the flow into this pipe and then down this direction towards the bottom of the filter, trying to get it, or bottom of the tank, trying to get as far from the suction filter as possible. But as you can see overall within the tank and their baffling and everything like that, um, not a lot of dead zones. It mixes relatively well, and then the overall results are pretty good. But like I said before, anytime we see this, we really know that we can reduce the size of those reservoirs a lot of the times, substantially. So this is the overall, um, or this is our application where we move them into the TNK 25. So we're taking them from a 60-gallon tank down to a 25-gallon tank. So with um, uh, substantial cost savings on the oil and the weight savings and everything like that. So their current 60-gallon tank weighs approximately 121 pounds, and the TNK 25 weighs 45 pounds. So saving 70 to 80 pounds right off the bat in just the tank material itself. And then approximately a 30-gallon savings um, of fluid. So as you can see at 48 gallon a minute, this is really right where that 10K uh, tank is designed to flow. Um, has a diffuser on it, so it does a really good job of radial in the TNKs. It does a really good job of radially dispersing that fluid, and again with 30 gallons less fluid, it's matches the performance of the current really dramatically oversized tank. And then back where we were at before, um, you know from a oil and steel weight savings perspective, 604 pounds. So that's a ton of weight when you're talking about a municipality vehicle that goes in and out of towns and is always up against weight restrictions and things. And Oil cost savings, $210. CO2 reduction savings from just the oil alone is 720 pounds of CO2 per machine. So these guys are making about 150 trucks a year, and they have three other platforms that they might add this to that will take it up to 600 trucks a year. So at 600 trucks a year, you'd be talking about a relatively substantial amount of CO2. 432,000. Wait a minute. How many? Yeah, so 432,000 pounds of CO2 saved from entering the environment every year from just the oil savings alone. That's something substantial when it comes to, reducing our carbon footprint and keeping our planet green and habitable for a long, long time going forward. And then the overall savings for the total reservoir was about $770 for that machine. So really saving them, substantially all across the board. This next thing we want to talk about is the what we're getting ready to launch coming in the next couple of quarters here. So we've been partnering with our parent company, Hydac, who also makes hydraulic oil coolers, and we're making basically a complete fluid conditioning unit. We call it the FTC with the filter tank cooler. We've already done a couple of different applications for these. The most notable one, they had a 25-gallon reservoir. We were able to take them down to this 7-gallon reservoir with all of these components and everything built in. And this unit actually bolts in the exact same place as where their 25-gallon reservoir was before. And they used to have a remote mounted cooler on the machine itself. So here at Schroeder Industries, with our filter systems group, we really have the um, um, with our filter systems group, we really have the ability to do this type of assembly work and everything like that. We have the know-how, so we're kind of reaching out into these type of platforms as well. Um, Extend that knowledge into some higher value work with our from our filter standpoint, and taking it into a system or a manifold kind of cell going forward. So the category list on the right that we use to kind of get out our optimization goals, find the information on what we're using now. That coupled with some 3D and 2D drawings is generally about all we need to get going with an optimization and trying to better our customer systems and try to work with our customers as partners going forward. Um, so that's all that I have right now. So if you want to reach out to Sims, they'll have a copy of this form, and if anybody else doesn't have it, feel free to email me, and I can get that over to you. We had one other question put in the chat. Do I have a calculation for the CO2 per pound of steel? Yes, I do, and I can add that into future presentations. I just hadn't had a chance to update this one, being out of town some this week, but that's something that we'll add going forward. And then we want to also, when we save that much weight, we also wanted to kind of help equate that to fuel savings and things within our calculations, because every pound of you save on a machine is the more fuel efficient it becomes, especially for say a service truck or something like that. Like with that FTC cooler group we just showed at the end. But that gets a little dicey as far as the calculation goes. So we're working through some of that stuff to help our customers better understand our advantages and how much we can help them reduce their carbon footprint overall. And a lot of this stuff is new to the customers too. So you kind of got to get their buy-in on how we're all laying it out. And then what are you using for cost of steel now? Well, that changes daily. So I don't exactly know the number off the top of my head, but it just depends on um, what we get quoted from our, we kind of get when we calculate that out for our customers, we look at what tank they're using and what thickness of plate and everything, and we kind of make it a one-to-one kind of thing. So, but I don't know exactly what that number is off the top of my head, but it's more than it was a year ago. I know that much for sure. So, but that is a good point. There are a few applications a couple of years ago that we quoted steel tanks in or plastic tank reservoirs versus the customer steel tank, and the delta of savings at that time wasn't high enough for them to make a switch from their current steel tank to the rotomolded composite reservoirs. But since then, some of them have came back to us, whether it be because of availability, just not being able to get their current steel reservoirs, or because of cost, have came back to us um, to reevaluate the rotomolded reservoirs and go back down that line. And I know for a fact we're looking to close one of those next month, where 2 years ago we weren't competitive because steel prices were so low, and now we're looking a whole lot better. So feel free to reach out to me, and if you have a customer application, we can walk through it together and see what we can do. Or any member of my team, Dan Brooks is on the line as well. He's our application engineer for hydraulic and lube here, and then Jeremiah Allshouse, he's our product manager for Elements, and he can help you work through savings on energy savings through eDrive media and that kind of thing. So that being said, that's all that I have for today. I think this was scheduled for an hour and a half, but I'm an overachiever and I got through it in an hour and 10 minutes. So I'm sure none of you guys will fault me for that on a Friday. Um, are, are there any other questions? At this point, you can unmute yourself if you want to ask them, or you can put them in the chat.
Jeremy, I think you missed one from Jeff. I said, what supports the media pack and the outer support tube in some distance away from the media? Jeff, what product were you talking about?
He was talking about
he did address it, Bernard. Thank you. The AFT, it just looked like it sat off, but there's some ribs built in. I think you said plastic injection molded, right, Jeremy?
Yeah, it's an injection molded rib support tube.
Makes sense.
It actually locks together in two different in 4-inch increments. So we have like a 4-inch AFT and that's good to like 20 gallon a minute, and then an 8-inch AFT that's good to 40 gallon a minute. So and then we've kicked around the idea of adding a 12-inch version, but we'll see as we move along with that if that's necessary. So
Perfect. Thanks.
thank you.
And just one thing to think about, guys, we've and ladies, we've had a lot of projects, and when you do a project review, we see application after application where in the past, didn't matter if it was Heideck or Schroeder, our filters in the return line application would never be considered. They were too expensive. But when you package the whole thing, you bring a value proposition to the customer, one part number, one purchase order, one transaction, one responsible party. We get closer to the design of the machine, which over and over again makes a huge difference. It's a longer sales process, but we don't get kicked out. But we open up the door to applications we never ever see or could never compete in before. And that is a huge change. And instead of selling when we could compete, a $40, $50 filter, we're selling a $400 to $2,000 subsystem. So it's really an advantage, and we need to jump on it while it's still our advantage, while we're still the only people making them in-house and doing it the right way. But just thoughts to think about on the commercial side.
Yep. Thank you very much, Gus. Anything else? All right, everybody. Well, if that's it, we wish you a wonderful weekend and have a happy Friday, and we'll talk to you later. Thank you.